This is an introduction to VLSI design, and today we will talk about adders. So in the outline, we will first check the single bit addition. We will introduce multiple design for it, and then we will dive through different types of adders like the carry label adder, carry skip adder, carry look ahead adder, carry select adder, and carry increment adder, and then we will end up with the tree adder. So for single bit addition, we have a half adder and a full adder. So the half adders has two inputs and has two outputs. The full adder has three inputs and two outputs. Now the outputs are the sum and the carry out. The sum is the XOR between A and B, and the carry out is the AND of A and B according to this truth table. So if you add 0 and 0, the sum is going to be 0 and the carry out is 0. If you add 0 and 1, the sum is 1 and the carry out is 0. If you add 1 and 0, the sum is 1 and the carry out is 0. If you add 1 and 1, then the sum is 0 and the carry out is 1. For the full adder, when you have three inputs, you also have the sum and the carry out as the output. So now the sum is A XOR B XOR C, or simply the odd function. And the carry out is the majority function of three inputs, which is going to be like the voting for three inputs. The function will be AB or AC or BC. So let's do it for according to this truth table as well. So if you sum up 0 and 0 and 0, now the C is actually the carry in, and the A and B is the inputs. If you add 0 and 0 and 0, the sum is 0 and the carry out is 0. If you add 0, 0 and 1, the sum is 1 and the carry out is 0. Similarly for 0, 1, 0, the sum is 1 and the carry out is 0. The 0, 1, 1 is the sum is 0 and the carry out is 1. For 1, 0, 0, the sum is 1 and the carry out is 0. 1, 0, 1, the sum is 0 and the carry out is 1. 1, 1, 0, the sum is 0 and the carry out is 1. 1, 1, 1, the sum is 1 and the carry out is 1. You can also think of it as adding the numbers and the result and decimal, and then convert it back to binary. So for example, if you have 1, 1, and 1, the addition of 1 plus 1 plus 1 is equal to 3, and 3 in binary is actually 1 followed by another 1. So it's also good to know that for the sum, you are actually doing the odd function, where you basically count the numbers or check the number of ones if they are odd or even. Since this is the odd function, what happens? You count the number of ones, so it's not odd, so the output is 0 in the sum. It's odd, so the output is 1. It's odd, then the output is 1. The number of ones here are even, so the output is 0. The number of 1 is odd, so the output is 1. Here, the number of ones will be even, and the last case, the number of ones are odd, so the result of the sum is equal to 1. And the carry out, as we mentioned, it's the majority function where you vote the zeros against the ones, and whoever wins will be the result. So here the winner is 0, here the winner is 0, here the winner is 0, the winner here is 1, the winner here is 0, and the winner for the voting here is 1, and the winner is 1 here, and the last case is obvious, it's going to be 1. So we looked at the table from different point of views. So also, when we say the majority functions, as I told you, that it means that the output is 1 if the number of ones is more than the number of 0. And the opposite of that is the minority gate, and the output is 1 if the number of 0 is bigger than the number of 1. Now, it will help us to know that the opposite or the complement of the majority is the minority. And the complement of the minority is actually the majority. So we said that this is the function of the majority, AB or AC or BC. The minority is A bar, B bar, or A bar, C bar, or B bar, C bar. Now, we will introduce the propagation, generation, and kill signals. This is very critical for the adders. When we look at different types of adders, we will see that they are important to understand. So, for a full adder, we define what happens to carries, and we put more emphasis on the carries more than the sum, because it will be the bottleneck for us when we calculate the delay. So we care about them more than the sum. So we try to find the generate and the propagate and the kill signals of the carries in terms of A and B. So for example, if you have this truth table, these are the inputs A, B, and C, and you want to get the generation, the propagation, and the kill signals. We get the sum and the carry out from the previous slide. Now, when we say generate, we are actually trying to find when we will generate a carry in the next stage. Or similar thing for the propagation. When are we going to propagate a carry from this stage to the next stage? And for the kill, when are we going to kill this carry, meaning that we are not going to propagate it to the next stage? That's the idea. So to generate, you know that the carry will not, or the carry will not generate unless you have 1 and 1 in A and B. So if A is equal to 1, and you are adding 1 to 1, here the result is going to be 0, and you will have a carry generated. This is a newly generated carry. So now the generation signal is A ANDed with B. Because if you have the other cases like 0, 0, the output is 0 and there is no carry. 0, 1, the output is 1, there is no carry. 1, 0, similar, the output is 1 and there is no carry. So it only generates if you have 1 and 1 in A and B. And this is basically the AND function. It's also shown in this truth table, where the generate signal only happen when you have A equal to 1 and B equal to 1. And here is the generation. For the propagation, this is a better example. Whatever you're carrying, whether it is 1 or 0, the 1 is more obvious. So if you have a carry n equal to 1 and you have A and B, A is 1 and B is 0, or vice versa, then the result is going to be 0, and you are propagating this carry to the next stage. Same idea, you propagate to the next stage. Same idea, you propagate the next stage until you find it in the carry out. So the propagation happens only if you have A is equal to 1 and B is equal to 0, or A is equal to 0 and B equal to 1. This is why the propagate signal is actually A XOR B. Remember, 1 and 1 is actually the generate signal. So A XOR B is actually the propagate signal, and you can see that the propagation is equal to 1 only when A and B are different than each other. So for the kill signal or the kill of the carry, it happens when you have 0 and 0. So if we say that you have a carry 1, and then the A and B, they are 0, 0, then what happens to this carry? It's going to be in the sum, and there is nothing generated in the next stage. So basically, we kill this carry and we make it drop in the sum. So that's basically the idea. And as you can see, it's A bar ANDed with B bar. So, or you can write it down like this: A bar ANDed with B bar. This is the kill signal. You can also apply the model law where you have full bar here, and you would say that it is A or B like this. If you now it's important for the propagation to treat the 1 and the 0 the same. So either you are propagating the 1 and the carries, or you are propagating the zeros. Notice that this one for this 0, it's propagating to the next stage, and then propagating to the next stage, propagating to the next stage, and so on. Propagate signal is very important. Each one of them actually has its own usage. But the propagate, if you know for a fact that this carry here is going to propagate all the way to the carry out, then you don't have to wait until you reach to this stage. You can go directly and maybe continue for other stages. And we will see some type of adders based on this idea. So now, after introducing the basics of the single bit addition, let's go to the designs. So this is the first full adder design, where the sum is basically the XOR, and the carry out is the majority. We said that it's actually the minority bar, meaning that it is the minority as we stated, and then you have a full bar. And now we took the carry n as a common factor. We choose the carry because, again, it's the critical input. And we have a full bar for this function. Now, how to design this? You design this using the CMOS design. So for the carry out, since we have the bar overall, the function, we take whatever below the bar and we design it in the pull down. You can see that the A bar and the B bar, they are in series. Those two are in parallel, series with the C bar, and then the two groups, they are in parallel, as you can see here. Now for the pull up, we can do the duality that you are used to, but there is a symmetry, actually, property between the pull up and the pull down, and you can check it against the truth table one by one, and you will find out that really this gives you the carry out, whether you are working with any input combination. Now, for the sum is actually the XOR. Now, we know that the function of the XOR is actually the odd function. So we can get the even function, which is basically the X NOR, and we complement. So the XOR is actually the X NOR complemented. And then we design it here. So you can see that for the sum, for example, we have A bar, B, and C. A bar, B, and C, which is this min term. This is actually when the sum is equal to 0. So what we are doing is we are looking at the 0. Or you can do it by having the XNOR function, get the min terms for the XNOR function, all bar, and those min terms is the one that you are going to design below. Or quickly, since we have the truth table, you can have these min terms and you try to design them in the pull down. So the first one is A bar, B bar, C bar. So you have it here, A bar, B bar, C bar. The next one we have A bar, B, C, A bar, B, C. The next one is A, B bar, C, A, B bar, C. And the last one is A, B, and C bar. So you have A, B, and C bar. And notice that we are sharing the transistors, because these min terms, you're supposed to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 transistors in the pull down. But when you count here, you'll find them 1, 2, 3, 4, 5, 6, 7, only 8. So actually, we share some transistors to reduce the the number of them in the pull down. And again, we have this symmetric behavior in the pull up, where you can do the symmetry in the pull up, and it works fine, and you can check the truth table to make sure it is correct. That's the first design. Now, in the second design, what we did is we factor this in terms of carryout, or more specifically, in terms of carryout bar. So we know that the carryout bar, we know the carryout is actually what we discussed here before, that it is actually the minority all bar. That's the carryout. So the carryout bar would be the majority. It would be the majority all bar. That's the carryout bar. Now, what happens in this design, the idea is that we are trying to find the sum, which is AX or BX or C, as or in terms of A, B, C, and also the carryout bar. And to do that, we can clearly see it in the truth table. Now we added this column, which is the C out bar, which is the complement of the C out. Now we try to get the sum in terms of these four values. And you can see that the sum would be 1 if you have A, B, and C, which is this case, A, B, and C. So we have 1. Also, we have these three ones only if the carryout bar is equal to 1, and at the same time, one of these inputs, A or B or C, is 1. So here we have this one. Since we have these, we can get 1. Here we have this one here. So we get this one. And here we have this one. And this takes this out because, yes, we have the carry out equal to 1, but A, B, and C, all of them are 0, 0, 0. So this doesn't satisfy this term. So that's how we get it. Now, in the design, the good thing is that we design first the carry out by this, similar to what we've discussed in the previous design number 1. But now the inputs are actually A, B, and C, since they are the majority, and we are getting the C out one. If you want to get the C out, you simply add this invert. If you compare this design to this one, you would see that they are exactly the same, except that the inputs here are bar, because you are doing the minority bar, but here they are actually with the normal polarity, because you are doing the majority bar. Now, after this, you get the sum by having A, B, C, and they are in series here, A, B, C, or A or B or C ended with the C out bar, and this is what you have here, A or B or C, those three transistors. This is A, and this is B, and this is C, ended with the C out bar. And again, we have this symmetry in the pull up. Now this will generate the sum bar for you, and you can get the sum by doing the invert. Yeah, so basically that was the sum bar. This is what we got here. This is basically the sum bar. You can get the inversion to get the sum, since we are doing the pull down design that is connected to the ground. This is what I explained here. It's written as compound gates. It's the same idea. It's basically exactly what we are saying here. So it's the C out bar is actually going to be AB or AC or BC, and we can rewrite it like this: AB or AC. Can take this carry as a common factor. And this way we did it here. You have A or B, and then ANDed with the C, and then you have B and or A and B in the second AND. And now we can just do the ORing between those two terms, and then all bar. This is by introduced by this bubble. for the second one, we have A and B and C. That's the first AND for this term. And the second one, you have A or B or C, which is this OR, followed by AND, ANDing for the carry out bar. And now you get the, do the ORing, this OR, to get S bar. And if you want S, you just do the inversion. That's basically this second design. And to do this design, actually, we did the sizing where we never cared about the sum circuit at all, because we know that from the carry in, from having the input of the carry in until you get the carry out is actually the bottleneck. This is why we care about this path here that has the carry in up to the carry out. And the rest we make the sizing one, all of them. So here we did the proper sizing, and even we make it even larger, where here you have 4 and 4, and this is better with this, so it's 4, and here we double everything, 8, 8. Only because we care about the carry in. So this way we optimize it. The sum is okay, it's not a bottleneck for us, so we left it with the minimum sizing, which is equal to 1. The third design, we are having the complementary pass transistor logic idea, which is basically slightly faster but has more area. And to do this, you apply what you learned in logic design when you study the multiplexers. One thing that you studied there is actually the design using a multiplexer, or the design by Mux. And if you have a truth table with 3 inputs, notice that we change the polarity a little bit, so, or we change actually the order. So we have C and followed by B and A. So A is the least significant and the C is the most significant, because we want the C and B being the selectors, and A, we see the relation between A and the sum, A and the area. That's basically the idea. So we divided this truth table into 4 regions, and now we compare for C equal to 0 and B equal to 0, what happens to the carry out? So you compare and you find out that the carry out is going to be equal to 0. So here we can say that it is 0. Let me put it like here. And here it's actually the same as A when the C is equal to 0 and B equal to 1. So it's basically C. Sorry, it's actually A. You're comparing A to the carry out. And here is again A. And the last one is always 1. That's what you do for the design values. So since this is a CBL, we said that in CBL you have the output and the output bar. So you have the C out and the C out. Well, now going back of this inverter, we have the C out here. And this C out is actually the one that we are interested in this column. And we see that, okay, when you have 0 and 0, so when you have C bar and B bar, the input should be 0. And this is the ground. When we have B, C bar, which is this case, B and C bar, we should give it A. Similarly for the other case, when you have C and B bar or C bar, B, both of them, B and C bar, or B bar. And with C, both of them get A. And in the output, this is supposed to be A, I don't know. And the last case here, when you have C and B, you have B equal to 1 and C equal to 1. Now you give the VDD in the input. This way you did this design. And notice that there is, you can do it exactly the same way here, but now you will have the C out bar here. But there is actually a simpler way to do it, where what you do here is notice that we have, since we chose C and B to be the selectors, we say that this is C bar, C, C bar, C. Again here, B bar, B, B bar, B, B bar, B, B bar, B, one after the other. And then you do this based on what we just mentioned. And what happens in the next one here, if you do the same order that I just mentioned, Then you flip everything. The ground will become VDD here. The A will become A bar, and the VDD becomes the ground. This is for the carry. We will do the sum, basically doing the same thing. So we have the sum bar, then this is the sum. And in the sum, we have the ones in these minterms. Last one here. So you have, for example, 1, 1, 1, which is A, B, and C. This is for the sum. So you have A, B, C. We have done this now. Or let me write it this way. And for this one, you have C, B bar, A bar. So you have A bar, and then B bar, which is this one, and then C. So you get to the C to get to the S. So you did it for this term like this. For this one, this is what we got. Now for this one, it's A bar, B, and C bar. So it's A bar, B, and then C bar, which is this one. Now you reach to the S. The last one, which is A, B bar, C bar. So it's A, and you have B bar and C bar. Going to this. So for S, you will have 4 baths to reach to this point, indicated by the ones. And similarly for the S bar, if this is S, now here you have S bar, so you look at the zeros, and you will have also the remaining 4 baths. Again, we did the same idea that we've done in design number 1 and even number 2, where we can share the transistors. So that's the third design. The fourth design is basically using the dual rail domino, which are very fast but large and power hungry, and they are used in very fast multipliers, for example. Now, we know that dual rail domino, and we discussed this in a previous video. So we get the C out, and you know that this is the majority. Remember, in the domino, we don't care about the full bar. We just design right away. So this is the majority, and you design it here. As you can see, the A, B series, A or B, they are in parallel, followed by the C. The C out bar is actually the minority, and we do the same here. Now, for the S and S bar, notice that I chose the S to be in this side and the S bar in this side, and that's okay. We can do the other way around as well, as long as we give the correct function either. So this is S, AX, or BX, or C, and these are the 4 min terms that represent the ones in the S. These are the min terms. So for example, the last one is A, B, C. This is the last one. And you can see it as well here, where you can have A, B, and C. That's the first one. We have A bar, B bar, and C. So we have this one. We have A bar, B bar, and C. We have also the A. We have A, B bar, C bar, and the last one, A bar, B, C bar. This is A bar, B, and C bar. So as you can see, all these 3 paths go to the S. We can do the same for the S bar, where S bar is equal to A, X, or B, X, or C, or basically this is the X known, and these are the 4 min terms for it, and you can follow the path in this similar way. So now, after we've done the single bit addition, And basically what we have done is we designed the fold adder in many different ways. We give you 4 different ways. And if you go and check your book, you'll see some of the details. Like for one of the design, you can see actually the layout, how you are doing the layout, the exact layout of the design. I believe it's design number 2. Now let's jump to having the different types of adders. Now we will move from a single bit to n-bit adders. And the first type is the carry propagate adder. In the carry propagate adder, each some bit depends on the previous carries. So if you have this, for example, and we explained this before, when we talked about the carry propagate, what you do is you sum and then you do the carry, and then you sum again and so on. What happens here is now you have n inputs, and in your book, sometimes they start from 1 to n, sometimes they start from 0 to n minus 1. So be aware of this. So now we have n inputs in the A, we have n inputs in the B, and we have a single bit in the carry n. And now you have n inputs in the sum and a single bit in the carry out. This is what we call the carry propagate adder. From that, we can do the carry ripple adder, which basically having this, for example, here in this slide, we have 4 bits. So what happens here is that whatever carry out you have for this first stage, you connect it to the carry n of the next stage. The carry out connected to the carry n, carry out connected to the carry n, and now you have the carry out for a 4-bit addition of A and. So this is the simplest design. It cascades the full adder, as you can see. So what's inside this circle is one of the designs that we've just discussed. 1 or 2 or 3 or 4. So you have here until we get the carry out. And so you can see here why we care about the carry. In the carry ripple adder, the carry is actually the bottleneck. So you have to wait until this is finishing, until you get the last carry out. So the last carry out is actually depends on the first one. But this sum is based on those 3. This sum based on only those 3 and so on. And the last sum is based on the carry number 3, B4, and A4. So this is the bottleneck, and this is why we care about the carry, and we also define the generation, propagation, and kill signals for them. Now, know that you can do the inversion. Sometimes this is useful, and especially if you do the CMOS design where you have the sum and the carry, both of them with their output bar. So you have a bubble here, and you also have a bubble here. If that's the case, then what happens is sometimes it's useful to have the first, it depends on the design actually that you adopt, whether it's design number 1, 2, 3, or 4. Or there are many actually designs that we didn't discuss. So based on the design that you are using, the first stage where you have A1 and B1 have the inputs are normal and the outputs they are actually complemented. Now the next stage is the other way around. The inputs actually have bubbles in the adder. Now look, focus on the circles only. So here they are normal, and here we have bubbles. Here we have bubbles in the input, and here we have normal outputs. Now, once you do this for 2 stages, you just copy and paste them for the rest of the number of bits. Since you have bubbles here, notice that this bubble, you just goes right away as it is in the next one. For the inputs A, B, or this sum, if you wanted, you can add an inverter to get the correct polarity that you want. Now, the beautiful thing about this, the critical path that we care about could be shorter, because you don't have to add an inverter, and then again you add an inverter here to enter it to the second full adder. So as it's said here, it eliminates the inverter and use inverting full patterns. Now, coming back to the generate and the propagate signal. We have an equation that's often factored into B's and G's, or the propagate and generate signal. So to understand this, let's have the base case, and then we discuss the generate and propagate for the grouping. The base case, meaning if you have a stage, a certain stage, maybe stage 0, stage 1, stage 2. Let's have an example here so you understand. If you have 1 and 0, 1 and 0, and 1 and 0, and 1 and 0, that's A, and this is B. So for a certain stage, for this stage, you can generate its generating signal and propagation signal. So the generation signal for it is 1 ended with 0, so it's equal to 0, and the propagation is 1 XOR 0, which is equal to 1 for this stage. For the other stage, you can do the same, and this one, or also this one. So for every one of these stages, you can get the generation and the propagation signal in parallel at the same clock cycle. So you get all of these without taking much time. And also you have the base cases when you have the generation from 0, which is the first generation. The first generation meaning that what's in the carry right here. So initially, it's supposed to be the carry in. Sometimes the carry in is 0, sometimes the carry in is 1. So whatever carry in, you have it as the first generation. The first propagation is actually equal to 0. It's actually meaningless. So you just started, there is no propagation. So we assume that it is equal to 0. Now for the generation and the propagation grouping, we will start with the easy one, which is the propagation, meaning when are you going, if you are asking about this stage here, when are you going to propagate the carry to this stage? It happens if you have the propagation in the previous stage. Now let's take this one. When are you going to have a propagate in this one? It happens from the carry in, starting from the carry in. If you have a propagation here and you also have a propagation, this example is actually having a propagation here because it's 0 and 1 and A and B, and another propagation here, so it's 0 and 1. So this one will have a propagation. So basically the propagation from stage J to stage I, and usually J is equal to 0. So from the first stage, which is the first one here, to a certain stage, whether it's the first, the second, the third, or the fourth. So the propagation from, for example, from 0 to 2, it's the propagation into the same stage that you are interested in, and with the propagation from 0 to 1. Now go back to 1, this one. From 0 to 1, it's actually the propagation in 1 and with the propagation of 0. So you can substitute this one actually here. If you are interested in the propagation from 0 to 2, this example, then it is going to be propagation in 0, and with propagation in 1, and propagation with stage number 2. Basically, what we did is we substitute this value with this one here, and you get the propagation signal. So you can see from the propagation, when you talk about groups, starting from a stage to a certain stage, what you do is adding all the propagation signals from the beginning to the end. Now, if you look at this example, the end result is P0 ended with P1 ended with P2. And this is basically meaningless because we know that P0 is equal to 0. And 0 ended with anything will give you 0. So the propagation actually is interesting to us from the first stage on, So propagation from 1 to 2. So you have P1 ended with P2. This could be meaningful to us. So that's for the base cases and the propagation grouping. What about the generation? Or let's call it the group generation. We have the group propagation here, and we discuss it. And now, what about the group generation? Again, with the same example, we have 0, 1, 0, 1, 0, 1, 0, and here is 0, 1, 1. Now, if this is A and this is B, what we say here that if you are interested in the group generation from a certain stage to another stage, because in the base case, we say that the generation in this certain stage is actually the group generation from a stage to the same stage. We can rewrite it this way, like G00, B10, 0, or G11, B11, and so on. But here in the group generation, we have it from 0, for example, to 2, or to 3, or to 4. So you have, for example, from 0 to 2 in this example. We have from 0 to 1 in this example. We could have it from 0 to 4, or 0 to some other number. So how are we going to do this? The group generation, you can understand it this way. It's either you are generating the carry in the same stage, or you are generating the carry in a previous stage, and then you propagate it to the same stage. I'll say it again, and I will emphasize more the logic functions. So either you are generating in the same stage, or you are generating in a previous stage and propagating this generation to the same stage. This is the group generation. And here is some example. Again, I will do the same here. And I believe it was the other way around. Oh, this was 1, 0, 1, 0, 1, 0, and this is 0, 1, I think. Anyway, it could be anything. We take A and B. What happens, like if you want the group generation up to this one. So what happens is you say, it's either generated in this stage. So here, there was a generation. It's a new carry here. So it's either a generation here, or it was a generation here and propagated to this place. Or it's a generation here and it's propagated here and then there. Or it's a generated here, which is the carry n, and then propagated through all the stages. These are the, for this stage, these are the possible generations. So let's take the examples from 0 to 2. It's either generated in 2 or generated from stage 0 up to 1 and then propagated to 2. Again, for 0 and 1, either generated in 1 or it's generated in 0, which is actually the carry n, and then propagated to stage number 1. Of course, you can substitute this one here to get generation from group generation from 0 to 2, and this is what we did in this example. So this is the generation from 0 and 2, as we said, and then we substitute the value here, and then we distribute the P2 everywhere. So it's here and also here, and you can see it clearly that the generation from 0 to 2, either it's generated in 2, or generated in 1, then propagated to 2, or generated at 0, and then propagated through 1 and 2 to the stage that you are interested. So now we covered the group generation and propagation and the base cases. What about the sum? The sum simply is the XOR between the A, B, and the K. That was what we understand. Now we do the same thing here, but we rewrite it because we know that the PI, if you are interested in the sum in a certain stage, is actually equal to the propagation in that stage, which is the XOR between A and B. XOR with the carry at that stage. And the carry at that stage is actually the generation from 0 up to the stage that was right before. So it's basically the same thing for the sum. Now we will compile all these equations, all this simple mathematics, which actually it's very close to the proof by induction that you study in math or calculus courses. So uh, and now we will compile everything in the hardware into hardware. So here we will have three parts in any carry or in any atoms. You will have three parts. The first part is the BG logic or the bitwise BG logic. This is the base case. The B0 is equal to 0. The G0 is the carry in. Now for the A1, B1, A2, B2, A3, B3, and A4, B4, for each one of them, we get the B1, it's B and it's J. So here we get B1, G1, B2, G2, B3, G3, and B4, G4. And you can see here clearly that we can get all of these at the same clock cycle. Ready for one clock cycle, you get all of these results. Doesn't take much time. Now, let's move to the second stage. The second stage is the grouping of the generation and the propagation. The interesting or the important part here is the group generation. The group generation. So we have the generation from 0 to 0. The generation from 0 to 0 is actually the carry 0. The generation from 0 to 1 is actually the carry 1. The generation from 0 to 2 is actually the carry 2. And the generation from 0 to 3 is actually the carry 3. Now for the sum, we say that it is the generation, which is the carry, XORed with the propagation signal, which is A1 XOR B1 XOR C0. This is the definition of the sum at S. For the next one, you just the same thing, the C1 with the B2. This is the XOR, and here you have C2 with the B3, and so on. For the S4, you have the C3 with the B4 to get the sums. Now, what about the group generation? We didn't explain this, but we'll explain it clearly in the next slide. So now for the next one, we will explain, as I said, this one. So stage number 1 and 3 is actually the same stages for all the type of adders. The type of adders, they differ from one type to another based on this step or this stage. This step where you found out the group generations, G00, G01, G02, and G03, if you have 4-bit, this what makes one type of inverter differ than that. So let's start with the first type, which what we just discussed, the carry ripple adders. So the carry ripple adders, we have the same idea that we told you, which is you try to find the group generation from 0 to that stage. So it's basically here. What happens is we apply the same rules. Let's do it in here. Let's do it here, and then we verify. I went back to the slide before, so in the first grouping, it's actually the carry-in. So you just drop it here. In the B1 is here. Now the second grouping from 0 to 1, we actually find this out. We said that it is actually generations. It's either generated at stage 1, which is this one, or it is generated at stage 0, propagated to stage 1. So it's generated at stage 0 here, and then propagated at stage 1. So this is and and then it falls this one with an OR. This is the generation signal here. For the next one, we do the same. So you have AND OR for this generation. You do the ANDing of, based on this, we get the generation from 0 to 2. It's either generated at 2, or it is in the previous generation from 0 to 1, which is this point here, and propagated to 2. Similarly here, you have AND and OR. So it's either generated at 3, or it's the previous generation ANDed with the propagation signal here. And you can see that this is actually really the ripple adder, where you have the carry in going this way, rippled, and rippled, all the way until you get the carry out here. And this is basically, again, repeated. The same scenario is repeated. This one is repeated here. It's either generated at 4, or it is from the previous generation 0 to 3 and propagated to 4 to get the carry out. And this is exactly what we did here based on the equation. So this is actually what we are doing in the carry ripple addition. Notice that for the time, there is a time here in this stage, it's called TPG, which is the time for propagation and generation of the bitwise operations. And this one, this time, is the time for the XOR. Basically, we are saying that the time in an XOR, going through an XOR, is more than AND followed by OR. So that's the time here. Those two times, again, they are fixed for all the type of the adders. The only difference is in here. And as you can see, since this is a carry ripple adder, we are having for this stage from 1 to 4, we have this ripple behavior where you ripple through 1, 2, and 3. We count only these 3 for this stage. This one would be for it's actually within the XOR logic delay, and we say that it is T XOR. So here the delay is n-1 times the time of AND and OR, times this delay. And this is what we mean by the carry ripple addition. Now, instead of drawing the whole graph for every type of adder, we know that the difference is only here when you find the group generations. This is why we will introduce the BG diagram, and we will have it for the first type, which is the carry ripple BG diagram. Now, in the BG diagram, what we have here is we have the stages, for example, from 0 to 15. You can have it as the way you like, maybe from 1 to 4, from 0 to 4, from 0 to 15, from 0 to 16. It depends on how many bits you are working with. So if, for example, you have from 0 to 15 and you want to do the ripple from 0 to 15, what happens is you are supposed to get the group generations from 0 to 0, from 0 to 1, from 0 to 2, and so on, all the way until 0 to 15. That is the job of the BG diagram, is getting the group generations of the carry. So, in another word, this is C0, this is C1, this is C2, until C15. So, in the horizontal directions, this is the bit positions. In the vertical direction, this is the delay. This is the delay. So we will introduce this box, or what we call the gray cell. The gray cell is actually the generation equation. It's either generated in the same stage or generated in a previous stage, propagated to the same stage. So instead of drawing the same gate over and over, we will draw this simple box telling you that the generation comes from the same stage or from previous stage. That's it. You can see that there are 3 inputs here and 1 output, but we kind of make it simpler by having only 2 lines here and 1 line in the output. The 2 lines meaning that the generation happened in the same stage or in a previous stage, that's it. So the first one, it goes right away. The second one, which is from 0 to 1, it's either from 0 to 0 or generated at 1. This way you have from 0 to 1. And that's it. For example, if we have from 0 to 7, it's either at 7, so this is 7, comes here, or from 0 to 6. We already calculated. So from 0 to 6, concatenated with 7, let's say, you have 0 to 7 here. And so on, you can do it for the whole PG thing. So if we stopped here, if you want to continue, we would say 0 and 1 concatenated with 2, so it's 0 to 2, 0 to 2 with 3, 0 to 3, 0 to 3 with 4, 0 to 4. And notice that we are pushing this gray cell into the bottom at every stage. This is why we have this depth in the vertical direction, which actually represent the delay. We know that the ripple adder or the carry ripple adder is the worst adder in terms of delay. And this is why you will see its PG diagram, the one with the most deep PG delay. So it's very deep in terms of delay. Since we are working from 0 to 15, the delay, as we said, the delay of the ripple adder is TPG plus n minus 1, which is 15 here, plus TXO. So we have 16 from 0 to 15. So n minus 1 would be 15. That's the delay of the ripple adder. Now, as you can see, we introduced this gray cell. It's better to introduce the other cells as well. This is a simple buffer. Sometimes we use it to make the BG diagram easy to understand. We have the gray cell. This is the one that we just discussed. We have the black cell, which means like it's the gray cell, but there is something else more that makes it black. So the thing is, it is the propagation. We have the generation, which is similar to this one. We have also the propagation, which is basically the propagation in the same stage and the propagation of the previous stage. So if you add them together, you get the propagation signal, as you can see here. Now let's go to the next type of adder, which is the carry skip adder or the carry bypass adder. And the idea here is that the decision is based on the n-bit propagate signal. So if the propagate signal of, for example, a 4-bit adder is equal to 1, meaning that it is propagated at stage 1 and propagated at stage 2 and stage 3 and stage 4, this means that it can be propagated all the way to the output. So if the propagated signal is equal to 1, then the current carry is based on the carry from the previous stage directly, which is here in this block diagram. You can see that either you do the ripple or you skip, where you have this carry propagated all the way to the carry output based on the result of the propagate signal. So if it is 1, then skip. If it is 0, then do the carry, normal carry ripple. That's the idea of the carry skip adder or carry bypass adder. So to explain this better, this is what will, this is the PG logic that we explained before. Just put it here so you understand what's going on. So the carry ripple is slow through all the M stages. The carry skip allows the carry to skip over the group when the condition happens, which is the propagations of the group is equal to 1. The carry skip is beneficial when you have different grouping. or like, for example, you group bit from 1 to 4 together for A and B, and then followed by 5 and 8, followed by 9 and 12, followed by 13 to 16. So this is bit 1, 2, 3, and 4 are here. So there are 4 bits. 5, 6, 7, and 8 are here. This is 4 bits. 9, 10, 11, and 12, 4 bits here. And 13, 14, 15, 16, 4 bits right there. So you have actually the propagation signal from 1 to 4 coming from this box, which is basically a 4 input and circuit of the piece. So you take the first, the P1, P2, P3, and P4, and you put them as inputs for input and gate to get the output H. And this would be your selector for this multiplexer. Now, this multiplexer is the one that we just explained. Either you skip or you do the simple triple, where you have AND OR logic. This is the AND OR logic. And you have the XOR logic, which is this. Now, here you have the BG logic. This is the BG logic. And actually, you just need the piece. And you put them at the input of the 4 input. So the design is very clear for a certain stage. That's the first stage. Now for the second stage, you do the same thing. Either you skip or ripple, either you skip or ripple, either you skip or ripple. It's based on the propagation sequence. Now the beautiful thing about this, to generate these propagations is actually quite fast. It's only a 4 input AND circuit. So you did this stage either way, followed by a 4 input and circuit. So you get these results quickly. Now, if there is no skip, there is no skip here, no skip here, no skip here, and no skip here. This means that this group stage and this one, they don't have to wait for any carry from a previous stage. So they can all run in parallel. So this one, and this one, and this one, and this one, they will run in parallel if there is no skipping needed. So yes, you are ripple here for 4 bits, you are rippling here for 4 bits, you are rippling here for 4 bits, and you are rippling here for 4 bits. But since there is no skipping, you actually can do all of them at the same time. So now the question is, what is the worst case? So the worst case delay from bit 1 to bit 16 in this example. You ripple through bit 1 to 4. So rippling here. That's the worst case. And then you skip the middle two. So you skip here and skip here. And then you ripple through from 13 to 16. That was the worst case scenario. How is this happening? Let's do it detailed for the carry skip pattern. We have it at this time where you did the TBG, so you generated the P's and G's. So you spend this time, and you spend also 3 clock cycle for the T and O, multiplies by the T and O. So in that time, which is actually 4 minus 1, you already did this part. So these are already there, these signals in the red dot. They are already generated. Similarly here, and here, and here. As we explained, we can do those at the same time. The orange boxes in the top, we can do them at the same time. So at that clock cycle, these small red dots are already in place. So let's continue what will happen in the next cycle. In the next cycle, this one's supposed to start. So what happens is the following. You have the carry 4 and you have the signal already in the input of the mux at the cycle number 4. Cycle number 5, this sum will start to show up its first bit, and you have the carry number 8 going to the first of the input. So the mux done its job. Number 6, you are actually skipping. So you are doing this multiplexer. And you already generated 2 bits here and 1 bit here. Now, for cycle number 7, you are working in the first bit here, and at the same time, you generated the third and the second here. And then continue. The more bits you have, the more bits you have in the other adders. So there's an interleaving operation between these adders. So at cycle number 9, you will generate the second bit of the last adder, which is this one. And you also finish this addition. So the sum from 5 to 8 is already there. And the number 9, cycle number 9, you finish this one. This one's still waiting because you skipped and also skipped here. So it's still waiting for the last bit. So what happens for the last bit, you are actually going to add the last XOR, the T XOR, to generate the last one. And basically, we finished the addition from 1 to 60. Now, this carry out is for the other bits, if you have 17 and so on. And that was the delay, the worst case delay. So the worst case, you ripple, skip, and then you ripple. And as you can see, we find it to be 9. How did we generate? So we will get this 9 by applying what we just mentioned. So we ripple. The worst case is rippling in the first group and skipping the carry in the middle group and rippling in the last group. So if we say for a total of n bits that are arranged as k small in small bit groups. So in our example, we had 4 grouping from 1 to 4. That's the first group. From 5 to let me do it this way. The first group from 1 to 4. The second group from 5 to 8. And the third group from 9 to 12. And the last group from 13 to 60. So we have 4 groups, which is represented by K. And each one of these groups is 4 bits. So n small is also equal to 4. So each one of them is 4 bits. So in capitals, which means that the total number of bits is going to be n times k. In our example, it will be 4 times 4, which is 60. So notice that we started from 1 to 16, not 0. So what happened? To get the delay for this 9, we would say that we ripple in the first and in the last. The rippling in a 4-bit is actually n minus 1. So it is 4 minus 1, which is equal to 3. So it's n minus 1, where it is 3 in our case for each group. Why it's 2 here? Why we're multiplying by 2? Because we ripple into we ripple 2 times, 1 in the first group and 1 in the last group. And the remaining groups in the middle groups, what we are doing is k minus 1, which is the number of the groups minus 1. So it's 4 minus 1, which is going to be equal to 3. 2 times 3 plus 3 is equal to 9. To understand it in the what we explained, what we've done is ripple here, and skip, and also skip. This is what we did. So what happens since we ripple? So that's 3. Since we ripple here, that's 3, because it's 4 minus 1. Here is also 4 minus 1. And we skipped through 3 multiplexers, 1, 2, and 3 multiplexers. The last one didn't do anything to it because we are rippling. And that's why we have k minus 1. So to do this in the BG diagram, the first grouping, and the second, and the third, and the fourth, we do the rippling as one option. So the first option is to do the ripple, the ripple, the ripple, the ripple. Is that all the time? No. Sometimes we skip, sometimes we don't. So what happens is, sometimes we skip. This is why we introduced this multiplexer here. So sometimes we skip. whatever you have in number 0, we don't in our example, but if you have in number 0, then you skip right away. So either you ripple or you skip. Similarly here, either you ripple or you skip. Either you ripple through this or you skip. The last one, either you ripple or you skip. Now, if you are at this stage, or to find the worst case, that we said that the worst case is rippling through this one, and then skip, and then ripple at the last one. We can't go back because this is the delay or time. So we cannot go back to ripple. We go and ripple here. And that's why we have the blue cells here. We repeated the same thing, but we make it in this direction. Similarly for this one, we repeat it here, and this one we repeat it here, and this one we actually, in case we started from 0 to 3, we repeat it right. And that's the worst case. And there are so many cases that they are not the worst case. Let's say that you ripple everywhere. If you ripple everywhere and you never skip, then your design will work on like this one, and this one, and this one, and this one, and you will have this much delay from here to here. That's the delay that you are going to have. Let's say that you ripple and skip the first one and then ripple the last two. So you ripple the first one and then you skip So if you ripple and skip, then you need to ripple at the end. And this is going to be your worst case. And so on. This is why we have different methods. Let's have these, we can look at it to understand it. There's another way other than the VG diagram. As you can see that the depth of the VG diagram is less than the ripple adder. So this means that the carry skip adder is advantageous to us. So for this one, if you have 4 bits and you have 4 group, each one of them is 4 bits. So what happens is that you have 3 and 3, and you're skipping. So that's 3 multiplexers, which is also 3. So you have 9. Plus the initial TBG and the last T XOR. And you multiply the 9 by T O A O and O. If you have, for example, 4 bits and you have this mini group, which is 1, 2, 3, 4, 5, 6, and 7. So the worst case is ripple and skip the rest. Here is 3, and here is 3, and here we have 1, 2, 3, 4, 5, and 6. So it's going to be 9, 6, and 6. So it's going to be 12 instead of 9 if you have 7 groups. Now we will go to the other type, which is the carry select adder. The carry select adder is basically a trick for the critical path dependent on the late inputs, which is, he said X here, which is the carry actually. So in the first group, we just do the ripple. The problem is the second group, you cannot start adding unless you have the output of C4. So in the carry select adder, the keyword here is select, you add 2 times. One time, given that the carry C4 is going to be 0, and one time, given that the carry is going to be 1. We do this for any other grouping as well. So what we do here, at the time when C4 is available, the only thing that we're doing is just the multiplexer. So if C4 is 0, you get the result from here. If it is 1, then you get the result from here as the sum. Similarly for this one, and similarly also for this one. And notice the ripple here. we have a ripple between the groups. We have 4 groups, and between the groups, we are actually rippling. This is the carry select adder. So you pre-compute 2 possible outputs for the carry being 0 or 1. And then when the carry is available, it's a matter of selection. So it pre-computes n-bit sums. So you do the pre-computation here. And for both possible carries into n-bit groups, you do this. So for 0 and 1. And the proper carry is selected by the multiplexer, which is reduced to an AND OR circuit, which is this AND and OR. So you are actually rippling at the end. This is the carry select adder idea. The carry look-ahead adder. Now, what happens in the carry look-ahead adder? You are actually computing the generation from 0 to every single stage. And the carry look-ahead adder is the fastest adder. And what you do is actually you are distributing the piece for every generation until you distribute it among all the generation signals. And we did that actually previously when we talked about the carry propagation signal right there, which is here. We talked about it and we gave example here when we said we have the generation from 0 to 2. So what happens now? The carry look-ahead adder is doing this. So you are ORing 3 terms. 3 input AND, 2 input and a single term or a single letter. That's the idea of the carry look-ahead adder. And this is what we mentioned also here. This is exactly what we were saying here. So it's either generation or propagation from a previous generation, or a propagation from the previous generation, and so on until you reach to the base case. This is an example where we combine the carry look-ahead adder with the carry ripple adder. So it's kind of a middle ground. And here we have 4 groups. Each group, what you do here is the carry ripple adder. So we have a carry ripple adder here, carry ripple adder, carry look-ahead adder here. For each group, you have carry look-ahead adder, carry look-ahead adder, carry look-ahead adder, and the carry look-ahead adder. But we connect the groups together by a carry ripple addition, represented by the AND OR, AND OR, AND OR, and then AND OR. So that's the idea of this type of adder. We can use AND OR. We can also use the Manchester chain that is explained in your book. Now, how to get the BG grouping of the carry look-ahead adder? We introduce it like this one. So the generation now, we calculate the equation and we found out that it's either for a certain generation, it's either generation the same stage or the propagation of a previous stage. And this previous stage, it's either generation in the same stage or propagating from a previous stage and so on. So it will become AND or AND or AND or AND until you reach to the base case. This is the idea of the carry look-ahead adder. You can have the generation and also the propagation. The propagation will simply be an AND circuit. It is 4 inputs since we have the grouping for every 4 bits in this example. So we have 4 bits here, 4 bits here, 4 bits here, and 4 bits here. This is why we have the AND to here 4 bits. And also it's the same reason that we have AND OR repeated 3 times. So we can, instead of drawing this every time, we can represent it using a single small circle that is black. So either you are generating the same stage or propagating from the stage right before that, or the one before that, or the last one at the beginning. So you have 4 different paths for the generation. You have 4 different paths for the generation, which is this one, and this one, and this one, and this one. These are the paths of the generation. Now, we said the grouping, it's from 1 to 4, from 5 to 8, from 9 to 12, and from 13 to 16. And we do this one for the carry look ahead addition. So the carry look ahead addition here, and here, and here, and here can be done in parallel. They can be done in parallel. We said that there was a special carry look ahead adder that is mixed with the ripple adder, and this is the mixing that's happening right there, where you have this gray box, and there is a rippling, another rippling, and another rippling here. Now again, the BG diagram has specific job where you need to get all the generate signals. From 1 to 4 is already generated here. This is from 1 to 4. To add the 0 to it, you get here from 0 to 4. Now this circle that is white is actually a buffer. So it's directly giving you from 0 to 4. Similarly here, you are adding from 0 to 4 to from 5 to 8. So you have from 0 to 4 and then from 5 to 8. So you generate it from 0 to 8. And here you generate from 0 to 12. Similarly here from 0 to 16. Now the other ones from 0 to 0, that's direct. So you get it directly with this some small circle as a buffer. Now from 0 to 1, you need to calculate. So we did it as we've discussed this. Actually, it's called the Manchester chain, but you could consider it something similar to the carry look ahead adder. So it's from 0 and then you add 1 to it. So that's from 0 to 1. Here you add 0, 1, and 2. So you have from 0 to 2. And here you have 0, 1, 2, and 3. So you add from 0, 1, and 0, 2, and 0, 3 for each one of the stages. Now we repeat this in every stage to get 0, 5, 0, 6, 0, 7, 0, 9, 0, 10, 0, 11, and the last one 0, 13, 14, and 15. If you want the internal design of this box, you can refer to your book. Now this is for the carry look ahead adder. Now we will talk about the next type, which is the carry increment adder. And basically the carry increment adder, there is no new information. We are just repeating the same knowledge that we have known before. We factor the initial B's and G's and the final XOR out of the picture. So in the first step and the last step, we've done that part. We only care about the carry, where we introduce the PG diagram. Now, the gray cell and the black cell, we already defined them before. The only thing here, it depends in the carry increment adder. It depends on how you are doing the grouping. So here we did the grouping from 0 to 3, and from 4 to 7, from 8 to 11, and from 12 to 15. And we did rippling here, a ripple here, a ripple here, and also a ripple here. The idea of the carry increment adder, it happens below. So what happens is you just try to get the group generations correctly. So here it's from 0 to 0 directly. Here we did the rippling. So it's from 0 to 1. Here you have from 0 to 1, and you add 2 to it. So you have from 0 to 2. And in this box, you have 0 to 2 going here, and you have the 3. So you have 0 to 3. So you cover this one, this one, this one, and this one. Now about 0 and 4, 0 and 5, and 0 and 6, you actually have 0 and 3. So you add 4 to it, you generate it. You add 5 to it. Here, you have from 0 to 4. But you say here that you have from 0 to 4. Similarly, here you have from 0 to 7. And here you have from 0 to 11. Now, here is the beautiful thing about the carry increment adder. You don't have to do the rippling in those three stages because you are actually having the rippling in the black cell here. So here you have from 4 to 5. Here you have from 4 to 6, and here you have from 4 to 7. So if you want to generate from 0 to 5, you actually have from 0 to 4, and you add to that, or you concatenate 4 to 5. So this is from 0 to 3, actually. So from 0 to 3, and you have 4 and 5, and you can get this one. The same time as you are getting from 0 to 4. Similarly, here this is from 0 to 3, and you have already 4 to 6 here, and you get 0 to 6. Now, 0 to 7, you have 4 to 7, and concatenated with 0 to 3, you get 0 to 7. And this idea, you can repeat it here and also here to generate the group generations. You can note that this is very close to some of the ideas that we discussed before, and the delay of the carry increment adder, it's based on your grouping. So if every group is 4-bit, then it is n-1. In our example, it would be 3. And you have k-1, since you have 4 groups, it would be also 3. This is for the carry increment adder. Now, there are many ways to implement the carry increment adder based on the choices that you want. So you could have variable group size, where you have the first group, second group. So the first group is 2 bits, the second group is 2 bits, the third group is 3 bits, the fourth group is 4 bit, and the last group is 5 bits. And now you see some analogy here. So let's go back and to understand what's going on. So if this is 4 bits, you have 3 gray boxes. 4-bit, 3 black boxes. 4-bit, 3 black boxes. 4-bit, 3 black boxes. Also, since this is 4-bit, you have 4 boxes here. Since this is 4-bit, you have 4 boxes here. 4 bits, you have 4 boxes here. You can do the same idea in the next one. So you have 2 bits, so you have 1 box here. 2 bits, 1 box, 3 bits, 2 box, 4 bits, 3 box, 5 bits, then you have 5 box. And notice that the first one is gray and the rest are black, because you need the propagation as well. And since this is 2, you have 2. If you have 3, then you have 3 here. You have 4, then you have 4 bits. If you have 5, you also have 5 bits. Now, this might reduce the fan out in early stages. So the problem here is that here is fanning out to 2. Here you are fanning out to 3. Here you are fanning out to 4. And the last one you are fanning out to, as you can see, 5. To get rid of this problem, because as you increase the fan out, the capacitance increase, and if the capacitance increase, the delay also increase. So one way to do it is buffer out the ones that are not critical. So actually, you can push this one down. You can push those 2 down. You can push those 3 down. The rest you cannot push. If you push anything here, you will increase the depth, which means the delay. If you push this one, or this one, or this one, you are actually affecting the critical path. So these are factored out like this. Now, in the critical path, there is only the lowest number of fan out. So you have only fanning out to 2, fanning out to 2, fanning out to 2, until you reach to the end. And the end, you are having this fan out. You cannot do it. So if you want to fan out, the delay will increase. So that's the idea about if you have variable group size and how to fan out using the carry increment adder. At this point, we were reaching to the 3 adders, which is actually an idea that we discussed. It's just an organization. We're just enforcing this more. And we will give you different designs of adders, very recent. It's well known in the academia and the research. So the idea of the tree adders, it's a parallel prefix adders or a tree prefix adders where you compute the P and Gs in parallel at the beginning and also the sum using the XOR at the end. And in the middle, you have to do the group generation and the group propagation. One idea is you first compute all the 2 bits group for a binary tree, and then use these outputs to compute all the 4-bit groups, and then you do the 8-bit groups, etc. So as you can see, we are jumping in the vortices. The inputs, there will be the pairs of the P's and G's. So the inputs here in the prefix carry tree, they are the G's and P's. This is the first step and the second step. Oh, sorry, this is the first and the third, and this is the second. The first and the third, they are here. This is the first and this is the third. We are talking about the second. So the second depends on your choices. You are making different arrows. So if you first compute all the 2 bits group and so on, then you have certain type of error, and we will mention the name soon. The inputs are pairs of P's and G's. So these are the P's and G's. And the outputs are the new pairs of the group generation and the group propagations when you need it. And at each stage, you do what we discussed. The group generation based on this equation, the group propagation based on this equation. And if you need to do the idea of the carry look ahead adder, you can do it by doing what we discussed in the carry look ahead adder. So if you can, what you do is look ahead across look ahead. So recursive look ahead. If you do this, is actually the complexity for it is a big O of log n, and there are many variations on the tree adders, and we will start with the first one. The first one is called print conc, and this is the BG diagram for it. The idea here, we are talking only for all of the rest of the talk. We will talk only about the prefix carry tree or the tree adder here, this one. So what we did here, the carry computation order is odd bits, then even bits. So you have odd and then even. The logic levels is proportional to log 2 times log n minus 1, where n is the number of bits. The idea is first you compute all the 2 bits group. So you have 2 bits, 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 and 2 bits. And then use these two output to compute all the 4 bits group. So you do these 2 bits now together. So you have 4, you compute the 4, and you do these 2 bits together to compute the 4. You do those 2 and those 2 to compute the 4. And then you do the 8 by having, again, this 4 with this 4 to get this one, and then this 4 with this 4 to get this one. That's the idea. The maximum logic depth in the parallel prefix adder is the prompt conc. It's the longer calculation in time. It has the minimum number of nodes. So you have the minimum number of nodes inside the BG diagram in the print conc. At most 1 pair in any row. So in any row, at most you have 1 pair. You cannot have 3 pairs. So if you check any row, you'll have 2 pairs. It has this idea is to have a fan out of 2 at each stage. So you are trying to limit the fan out in the front. Now, what happens in the rest of the diagram? You are trying to get the rest of the group generation. So at this point, you get 0 to 3. At this point here, after we've done this, you get 0 to 7. And at this point, you get 0 to 15. What about the rest? The first one, you get it directly. The second one, you also can get it directly. The third one, it's not ready. So you have 0 to 1. You have to add 2 to it. So you need to add this gray box to get this. Now, this box is actually repeated here, here, and here. So from 0 to 4, since you have from 0 to 3, you need to add 4 to it. So you need to add this box.
But now you have 0 to 4, 0 to 5, you have from 0 to 3. So you add to that 4 to 5 to get from 0 to 5 here. Now you have from 0 to 5 here, you add to it this gray box to get 0 to 6. Now, as you can see, there is a repetition, kind of a repetition of this one here. And for the last one here, this covers from this grouping all to up to this point. And we know that we got 0 to 15. So now you need from 0 to 11, you have from 0 to 7, and you have from 8 to 11 here. So you get from 0 to 11. And we need to use the buffer to satisfy this property, the fan out of 2, to get from 0 to 12, so 11. Now from 0 to 12, we need to add this gray box of the 12, and here from 0 to 11. From 0 to 13 is actually, there is a repetition, the same repetition is actually right there. You can see that it is also here. So this one and this one and this one, they are there. And the last one, you just use this buffer. Even if you skip it, it's fine, it's the same. Buffer doesn't do much. That's the Brent conc idea. Now, this is the same idea that I just explained. I just put it in there slide to compare it easily with the next one. The next one is called Sklansky. So as you can see, I'm trying to compare Brent conc with the Sklansky. You see, it's kind of pushed the diagram upward. And by doing this, the idea here is the stages or the delay logic levels is proportional now to log n. So now the depth is shorter. So delay wise, it's even better. But so it has less logic depth, as I said, but the fan out doubles at each level. So now the fan outs here, it was only 2. Here, for example, the fan out is 3. And here it's 1, 2, 3, 4, and 5. And here you can see how many tests. So it's kind of doubling this. So every time you're doubling the fan out, that's its problem. So the fan out doubles at each stage. It should be optimized and buffered for critical path. It has fan out issues because of this. So yes, you have better delay in terms of depth, but you are having fan out issues in this class. Now compare this to the next one, which is the Coxstone. So if you compare this one with this one, the delay is increasing a little bit, but you are solving the fan out problem. So you can see here, the stages delay is proportional to log n. The fan out of 2 at each stage, so you are covering the fan out problem, but it has more PG cells inside, so it's almost full. Small PG cells, and it has long wires, so it has wiring issues. You can see that there's so many wirings here, and it's also widely used. That's the cog stone. And again, you can follow how do we generate the grouping here. If you compare this one with this one, what you are doing is you are actually taking care of the fan out. Now, next we have the Hand-Carlson. In the Hand-Carlson, the stages is log n plus 1, and it's a mix between the Coxstone and the Brent conc. You can see some of the ideas of the Brent conc, and there is also the wiring that comes in the Coxstone. It has a fan out of 2 at each stage, at most 1 pair in any row, and it trades the logical level for the wire length. Now for the next one is the Knowles, and it has certain types. In Knowles, it's very close to Coxstone, but it has some mixture with Sklansky. So it's a mix between the Coxstone and Sklansky. The stages are log n, and there is a fan out of 3 at each stage. So yes, we add a little bit of fan out, but we still have the wiring problem since we have the Coxstone mixture. The next one is called the Lander Fisher, and it's a mix between Brent conc and Sklansky. So as you can see, the new ideas there are just
mixing. And you can see clearly that the idea of front Kong at the end here, and at the beginning, 2 and 2 and 2 and 2 and so on. And the idea of the Sklansky where you do the addition of the fan out here. So the stage is log n plus 1, the fan out of n divided by 4 plus 1, and there is still some wiring there. So if you want to do comparison between those different types, in terms of delays, if we have this assumption where the wire capacitance is neglected, then the Coxstone adder is the best. And it's very obvious because the problem of the Coxstone was the wires. If you neglect the wire capacitance, then the Coxstone will win. And this what happens. We implement like in the research, someone implemented all of them. And he implemented for different number of stages where it is 16, 32, 64, and 128. And as you can see here, the minimum for 16-bit, this is in terms of delay, it was 9.4. The minimum for this one, this was 12.1, I believe. No, it was actually 11.5. For this one, the minimum delay was it was 14.9. And for the 128, we found it to be 18 plus 9. So basically, this one for this experiment, Lander Fisher was having the minimum delay. And if n equal to 16, it's the Coxstone. So the Coxstone wins only if you have n equal to 16, where you have the least number of wires possible. If you're adding more and more number of bits, then the wire problem becomes too much to win the delay race, where Lander Fisher in those number of bits is winning. To compile everything in a single graph. Here are the major three type of adders of the three adder taxon. We have the print conc, we have the Sklansky, and we have the Coxstone. Print conc actually cares, or the problem of the print conc is the logic level. You see that the worst delay of the three adders was with the print conc. The problem with the Coxstone was the wiring. It has so much wiring. And the problem with the Sklansky is the fan out. It has the extreme number or the extreme amount of fan out. Now, you can see the other types in the next figure, where you have the Lander Fisher with two types, you have the Horncastle with two types, and you have Knowles with two different types. This triangle is those types that we just showed. If you want to introduce any new, and by the way, in these figures here, the one that you see coloring, each one of them is showing you the delay. So you see the delay of the Lander Fisher, you see the delay of print conc, you see the delay of the Horncastle, you see the delay of the Coxstone, it's very fast. And it's not that clear, but it's there somewhere here. And the delay for the Sklansky is right. The thing is, if you have a new design and you have an idea and you try to implement a new PG diagram for a certain adder, and your design was here, it means that it's not good enough because Horncastle is better than this, because it's outside the triangle. If your new adder is at the edge anywhere, it means it is as good as one of these types. It has advantages and disadvantages. What you really would love if you have a new adder that's somewhere here in the middle, inside the triangle. So if that's the new adder, then this is amazing. because it will have less, it's like excelling in all three ends, in the logic levels, the fan out, and also the wire track. So the wire tracks here would be much less than the Cox cone. At the same time, there is not a lot of delay in terms of logic levels. The logic levels are very small, and the Sklansky is also there, and the fan out is good in. Notice that this is a 3D diagram. So this new adder is actually somewhere in this cube. This cube right there. So as a summary, the adder architecture offer area, power, and delay trade-off. You choose the best one for your application based on your needs. This is some of the end result, where we have the architecture of the carry ripple adder, the carry skip, the carry increment, the Brent Kong, Sklansky, and Coscon. For the carry skip and the carry increments, they are the stages, or the in small, where you have each groove has 4 bits. Now here are some classifications, but we said that the Brent Kong is the one that has the maximum number of or the delay depth is the worst in the Brent Kong. We said in Sklansky the fan out is the worst, and in the Cox Kong you have the wiring problem. This is based on these classifications. In the logic level, in the carry level, it's n-1. Carry skip n divided by 4 plus 5 if the n is equal to 4. The carry increment is n divided by 4 plus 2. In Brent Kong, it's 2 log 2 n-1. And in Sklansky, it's log 2n, and in the Cox Kong is the same. Now, this is for the logic level. For the maximum fan out, in the carry level, it's 1. Carry skip is 2. Carry increments is 4. In Brent Kong is 2. Sklansky n divided by 2 plus 1. And in the Cox Kong, it is 2. So if it is constant, it's always good. But if you have the first order of n, then in terms of fan outs, the Sklansky will be the worst. In the tracks, you can see that they are all 1 except the Cox Kong, where you have a lot of tracks. It's actually n minus n divided by 2. In number of cells, but within, if you look at inside the BG diagram, you see that the cells in the carry ripple adder is the lowest, which is n, and the carry skip it's 1.25 n, and the carry increment and Brent Kong, both of them 2n. Sklansky is 0.5 n log 2 of n, and in the Cox Kong is actually n log 2 of n. This is the summary of what we have discussed in the adder, and I will see you next time. We will talk about more combinational circuits. Basically, one of the easy ones like the comparators and also the multipliers. So I'll see you next time.